Um, Today, guys, what we're going to do is we're going to be talking about an application of Fermi's Golden Rule. Um, when I originally laid out Fermi's Golden Rule, um, I couldn't really figure out a good industry-related application at the time. You know, um, it kind of seemed to me that Fermi's Golden Rule was a behind-the-scenes thing that kept the atoms and their energy levels in balance. Um, it did answer my questions on Feynman's diagrams and coupling, but I was kind of unable to come to something in industry that, it directly related to. Um, but I now was able to find that. And one of the areas that Fermi's golden rule works well is with transistors. And kind of what I mean by that is not like regular transistors, that we would have in a circuit, but these MOSFETs that were made, they were originally discovered in the 50s, like 1959, and they started being used in electronics in the late 60s. But let's talk first about regular transistors and the problem with Moore's rule. In general, what are transistors? Transistors act as switches, and they amplify signals. That's what they do. So basically, in order to process a lot of data, let me just go down here to this picture here. We have to have a bunch of transistors that are basically operating as switches, and what we call those is operating in states. And the more transistors that we have, the more data we're going to be able to get out. And that's kind of the deal. So each transistor can produce a bit of data, as it's going between the states. But the more transistors that we have, the more data that we're going to get out. Now, the problem with this is that as we continue to make the transistors smaller and smaller, which we have over the and years, and that kind of gets into something called Moore's law, like kind of like keep etching into the surface. And the idea is as we continue to make them smaller, we had a couple of problems with them. Number one, they weren't acting in unison, so the signals weren't always, as we were joining them together, we weren't always getting out exactly what we wanted to get out for the data. And then the other problem with it is that they were getting very hot. So we required specialized heat sinks as we continued to go down. So what we kind of did is we kind of came up with this technology to invent this thing called the MOSFET. And what you're seeing here is you're seeing a simulated view of a transistor just overheating and releasing a lot of energy as it's moving from one state to the other. So what are MOSFETs? In general, we can kind of get a sense right here of this is like a simulated view of a MOSFET. And a MOSFET really has a semiconducting material, which is either N or P doped, meaning we dope them with atoms, and they're either pentavalent atoms or non-pentavalent atoms, meaning you're going to get negative or positive. And what you're seeing there with the pink ovals there, is you're seeing a source and a drain. And basically the electrons are going to move through the circuit going from the source to the drain. Once we have a switch that's located in there. Now, the thing is, with these MOSFETs is they're pretty good. Let me just go over to here for a minute here. I'm just getting up here, guys. Sorry. So MOSFETs have a very low RDS value, and really that's the total resistance between the drain and the source. And this results in lower voltage drops and therefore less heat dissipation for most low and medium voltage applications. There's no doubt that MOSFETs can get hot if you have not a low or medium, but more of a high voltage application. In those particular cases, you're still going to need a pretty good heat sink in there. But for most low and medium voltage applications, you're not having that same problem that you're seeing here in the simulation with the overheating of the transistor. So therefore, you're able to get a lot more of these MOSFETs, shrunk down to a size and put into these boards, these computer boards, than you would with average or regular transistors. So let me kind of go over to here now, and we'll talk in terms of this MOSFET a little bit here. So basically what's happening is we're going to hook up with it's made of a dielectric material, but basically what's going on here is we hook up this electromagnetic switch here that's going to allow the flow of the electrons between the source and the drain. And so the bottom line is that when the switch is closed, that means that at each point along, along the MOSFET, we're going to be at a potential in which the electrons can flow. But when the switch is open, as you're seeing in the lower diagram here, it becomes like an energy barrier, like right here. So we can consider this these electrons that are here, and it's like all of a sudden we took like it might have been like a slide all the way down, and we put a bulbous in it, and that bulbous there is a potential well, and the electrons can no longer get through. So that kind of makes sense. I mean, you don't want electrons flowing when the switch is open. You want them flowing when the switch is closed so that you can get the right data out to zeros and ones in the binary. So, but so this works really well. These MOSFETs work really well, and when they were first made and stuff. And, and we can continue to start to make them smaller and smaller. But what started to happen is that as we began to, continue to make them smaller and etch them onto the board, what happened is the distance here between between the source and the drain one was on the nanometer scale. And once that started to happen, we started to get quantum effects, because you're really talking. We were talking really that this distance here is going to be within the range of a few atoms, and what that does is you can see here that the electrons can't make it over the bulbous, but all of a sudden they're moving. They're right here, but all of a sudden they appear on the other side, and they're doing what's called quantum tunneling. So as these MOSFETs began to get smaller and smaller, we get this quantum tunneling effect, and now they're not reliable anymore, because now where you should be getting a 0, we're registering a 1, because we're getting a flow of current, even though the electrons should be pretty much stopped. Because it can't make it over that potential well, but they're tunneling through it. Now, what scientists have proposed recently, and this is work here that is done by Gunther M. Corey, and M.J. Rack, and this was in 1999, and what they proposed is that to put quantum dots between the source and the drain. And quantum dots actually can be man-made, and what they are is they act as they act kind of like a well, an infinite well where the electrons are they're stuck in there. And they get stuck in there because these quantum dots are made to have the same energy levels of atoms, that these electrons can exist in those energy states. And these quantum dots, they're made by what's called colloidal synthesis, self-assembly, and electrical gating. And there's an article below by Avante that explains how that they're made. But they're made basically at 100 nanometers. And what's happening is the electrons, they form a strong coupling, um, between the electron and these quantum dots, and the electrons move into them just like they would move into atoms, and then they get stuck in these energy levels or energy wells, and they become traps for the electrons. So it doesn't cut out completely electron tunneling, but it sure dampens it. So, and the scientists can make those quantum dots, you know, um, larger or smaller, based on these processes that Avante talks about in their article. So the dots can dampen the tunneling effect, and which would allow the MOSFETs to work on this nanoscale level. So the bottom line is that the etching can probably continue to a point, making these MOSFETs smaller and smaller, as long as we're pretty much developing quantum dots between the the source and the drain. So I really thought this was cool. It's a nice application to Fermi's golden rule. Fermi's golden rule was basically the fact that, when there's an electron or some electrical occurrence disturbs that atom by passing by it, and it affects the potential energy of it, that the energy levels have to change. But the bottom line is that there exist already energy levels outside of that atom, so there's a coupling between the old energy level and the new ones, and and that's kind of just there in nature, which is really neat. So this here with the MOSFETs is a new type of coupling, which is really pretty cool. That's really created an industry to form in space or somewhere in in our our transistor or whatever that we're working on, these quantum dots. And these quantum dots form a strong coupling between the electrons and allow the electrons to seamless transition into what we call it's like a prison for them, where they then it's going to take a certain amount of potential to get them out of the quantum dots, and until we actually open up that switch, those electrons are not going to get that. And again, some electrons will still they'll figure a way to tunnel through that material. You're not going to cut it out completely, but you're definitely going to dampen it. So that's really it, guys. But thanks, and I really enjoyed working on Fermi's golden rule, and I like the idea of this MOSFET application, with the quantum dots. That's it, guys. Thank you now.